Alright guys, welcome to this page of the notes. So what we're going to do here is we're going to start jumping into some of our example problems when it comes to solving a system of equations graphically. Now, we talked about how to graph linear functions in chapter 2 of this course. So I'm not going to spend a ton of time going over how we graph these equations. Of course, I'll show you all my work. I'll talk you through it, but if some point you're like, wait a second, I really don't know what's going on here, you're going to want to go back to chapter 2 and look at how we graph linear functions on a coordinate plane. And in almost all of these example problems here with graphing, I'm going to put my linear functions into slope-intercept form. That is the fastest way to graph these functions. So let's just jump right into it. Here's what we're going to do. I give you a system of equations. I have an x, a y, I have an x and a y. I need to put both of these functions into slope-intercept form. That means solve for y. So I'm going to subtract the x to the other side, minus x minus x. That's going to leave me with y is equal to a negative x plus 3. There's slope-intercept form for that one. I'll graph that function for you guys in green in just a second. To solve this one for y, I'm going to need to again subtract the x from both sides, minus x minus x. That's going to leave me with a negative y minus x plus 1. Problem. I need to solve for y. I do not have the y by itself. I need to get rid of that minus sign. You can do either one you want. You can either multiply everybody by y, or you can, you can either multiply everybody by a negative 1, or you can divide everybody by a negative 1. Doesn't matter which you pick. They both have the exact same result. It'll change everybody's sign. Divide by a negative 1, divide by a negative 1, divide by a negative 1, and I wind up with y is equal to x minus 1. I will graph that one in, we'll graph that one in red. That way we can tell the two equations apart. Here we go. These are now in slope-intercept form. My first one, this is my y-intercept. It is a positive 3. So I'm going to go 1, 2, 3. That puts it right there. My slope is a negative 1. That means down 1 and then over 1. So down 1 over 1 would put me right there. I could also go up 1 and back 1. Exact same thing. In fact, that just works so well. Let's do it again. Now that I've got a couple of points plotted, all I need to do is draw a straight line through those points. This is a linear function. I know it's linear because my variable x is to the first power. Linear function. Here we go. Let's see how this works. Oh, you know what? I'm sorry. Let me be much more clear, because we are looking for a solution. So actually, before I graph the function, let me just put all of my points in here. So I'm going to have one there and there and there, 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 and now we can graph those guys. Let's get those guys through here with the line. So it's going to there. Make sure, please, that you extend your line. Please extend your line all the way through the coordinate plane that I have given you. Sorry, let me slide this up a little bit just in case you're having trouble seeing it. There we go. Extend that line all the way through the coordinate plane. And also make sure that you put arrows on the end of it so that I know you know that that line keeps going in both directions to infinity. Let's graph the one in red. I have a slope-intercept form. My y-intercept will be a negative 1. That puts it right down there. And then my slope is a positive 1. That means a rise of 1 and a run of 1. Up 1, over 1, up 1, over 1, up 1, over 1. Put all of those points in there, right up through there. I could also go down 1 and back 1. That would do the exact same thing. It works so well, let's try it again. In fact, we're going to do it a couple more times all the way down through there. And we're going to connect those guys to the line. And awesome. Make sure you extend your line all the way through the coordinate plane. Put arrows on both ends so I know you know that line just keeps going. And what we're looking for is a solution. I'm looking for the point where these lines intersect, and I found it. It's right there. Now, according to my graph, it is at the point x equals 2, y equals a positive 1. So my solution is 2 comma 1. And you do, remember I told you on the previous page, you do need to know the terminology. This means my solution, this means my system of equations is consistent and independent. If you're going to be taking, if you're in my Algebra 2 class and you're taking my Chapter 3 test, there will be questions on the test where I ask you, what do we call a system of equations that has one solution? You will need to know consistent and independent. You need to be familiar with that vocabulary. That worked out so well. Let's try another one. I got a couple more here for you on this page. So let's go ahead and take a look at these. Maybe we can run through these a little bit faster now that we know what we're doing. You have a system of equations, and in order to graph this system of equations, I need both of those equations to be in slope-intercept form. That means solving for y. So let's go ahead and do that. I'm going to have a negative 4y is equal to a negative 2x plus 12. Divide everybody by negative 4. That means y is going to be equal to a negative 2x over a negative 4 plus 12 over a negative 4, which means I'm going to wind up with the negative signs canceling out. 2 divided by 4, it's going to be 1/2. So I have 1/2 x. And then, of course, 12 divided by negative 4 would be minus 3. Minus 3. We'll graph that one in green. My next one, I got to solve for y, so I'm going to subtract the 4x to the other side. I wind up with negative y is equal to a minus 4x plus 10. I can't have that negative, sorry, that doesn't really look like a negative sign. It looks like a dot. There we go, there's my minus sign. I have a negative sign. Change everybody's signs. You can either multiply everybody by a negative 1 or you can divide everybody by a negative 1. It'll have the exact same effect. Everybody's sign changes. Y is equal to 4x minus 10. I'll graph that one in red. Okay, so here we go. Green one first. Why not? Why not? We'll do green first. My y-intercept, because it's in slope-intercept form, y equals mx plus p. Y equals mx plus p. So slope-intercept, my y-intercept minus 3. All right, there it is. And then I have a slope of 1/2. That means a rise of 1 and a run of 2. Up 1 over 2, up 1 over 2, up 1 over 2. Just keep going. I could also go down 1 and back 2. That would have the exact same effect. It's the same slope if you do a negative 1 and a negative 2, because the negatives would cancel each other out and still have a slope of 1/2. So down 1 and back 2, down 1, back 2, down 1, back 2, down 1, back 2, down 1, back 2. Awesome. Connect all those dots with a line. Make sure you extend your line all the way through the coordinate plane. Put arrows on either end so I know you know that line keeps going. Graph the one in red. Slope-intercept form, negative 10. There we go. That one just fits. My slope is 4. That means a rise of 4 and a run of 1. 1, 2, 3, 4 over 1. 4 over 1. Well, I just found my point of intersection. We'll go ahead and keep going, though. 1, 2, 3, 4, 1. 1, 2, 3, 4, 1. 1, 2, 3, 4. Perfect. And let's see if I can draw a line through these guys. This one's steep. Heck yeah, I'll take it. That'll work. Make sure you extend your line all the way through the coordinate plane. Put arrows on either end so I know you know that line just keeps going. And we already said, pretty easy to see now where that point of intersection shows up. It is right there. That means that my solution is at the point, let's see here, what is that? That's going to be x equals 2, y equals a negative 2, x equals 2, y equals a negative 2. And again, because I get a solution, I get an ordered pair, that means that this system of equations is consistent and independent, because they're separate lines. Consistent, there's a solution. Independent, they're different lines. Where is it? There it is. Consistent and independent. slide that page on up. I got another one for you right here. Again, hopefully what you're doing is trying these on your own. So if you've already gone ahead and tried these ones and you're coming back now to check your solution, fantastic, awesome. That's exactly what you should be doing. So here we go. Once again, I just need to get these guys, solve them for y, slope-intercept form. It's the fastest way to graph a linear function. Here we go. I'll have to subtract 2x to the other side. So that's going to give me minus 3y is equal to a negative 2x plus 6. Okay, great. Then I need to divide everybody by a negative 3. So that means I'm going to have y is equal to, now a negative 2 divided by a negative 3, the negative signs are going to cancel each other out. But 2 divided by 3 doesn't divide evenly, and there's no way to simplify it, so I'll just leave it as 2/3 x. 2/3 x. Fantastic. Then I have a positive 6, which will also be divided by the negative 3, and 6 divided by a negative 3 would be a minus 2. Let's graph that one in green. One more. Solve for y, so I'm going to add 4x to the other side. That means I have 6y is equal to 4x minus 12. Great, okay. We're going to need to divide by 6. Well, let's write this one out. 4x over 6. Sorry. That should be a minus sign, not a plus sign. Minus 12 over 6. There we go. Okay. 4 divided by 6, again, doesn't divide evenly, but I can simplify that. I can pull a greatest common factor out of both of them of 2. If I do that, if I pull a 2 out of 4, that leaves me with a 2. If I pull a 2, 6, that leaves me with a 3. That's interesting. Very interesting, because I also had a 2/3 x over here. Something's going to happen here. Either these are going to be the exact same line, or they're going to be at the very least, I already know they're parallel lines. Remember, parallel lines have the same slope. If you're not familiar with that idea, head on back to chapter 2 where we talk about graphing linear functions, parallel and perpendicular lines. But parallel lines have the same slope. So at the very least, these guys are going to be parallel lines, and I am now immediately thinking, okay, either there is no solution, or if my y-intercept comes out to be exactly the same as this guy, then that means they're the exact same equation. I have an infinite number of solutions. Let's see what happens. A negative 12 divided by 6 gives me a minus 2. Well, there we go. Please notice that both of these equations are exactly the same equation. What I had done is I gave you the exact same equation, just in different forms. This one, everybody had been multiplied by a 2. I had multiplied all the coefficients by a 2. That's how I got this equation. But when you do the algebra, all that stuff drops out. Well, when you do the algebra, when you put them in slope-intercept form, all that extra junk goes away, and they're the exact same equation. So here we go. This guy and this guy are the same. I'll go ahead and graph them, but at this point you can already give me your final answer. You know that there is an infinite number of solutions, and that this system of equations is consistent and dependent. Dependent because the lines are the same. Let me make a quick note here while I am graphing these functions for you, and that would be this. If you were to, which we'll do in a second, if you were to solve this system of equations algebraically, which we'll get to, do you remember what's going to happen when you solve algebraically a system of equations with an infinite number of solutions? All of the variables will drop out, and you're going to be left with some sort of true statement. Maybe 0 equals 0, or -7 equals -7, right? Something like that. You're going to get a true statement when you solve it algebraically. As far as the graphing goes, I graph both equations. They turn out to be the exact same line. Here we go, negative 2, up 2 over 3, up 2 over 3, up 2 over 3. Did I do that right? I did. Down 2, back 3, same thing. Down 2, back 3, down 2, back 3. I like it. Extend your line all the way through the coordinate system. In fact, let me do the one in green as well, just so you can see, right? If you were to graph both of those guys, they would turn out to be the exact same line. So what that means, infinite number of solutions, pick any point you want to. You can pick any point that falls on that line, and that value of x and that value of y will be a solution to this system of equations. I have one more for you. Head on over to the next page. And here we go. Let's go ahead and do this last one here. This is the last one we've got as far as graphing goes. I'm going to need to go ahead and put these guys in slope-intercept form. So let's do that. At this point, we're probably getting very good at it. So let's see how quickly we can do this. Subtract 4x to the other side. Negative 2y equal to negative 4x plus 8. Divide everybody by a negative 2. Y is equal to negative 4 divided by a negative 2 would be a positive 2x, and a positive 8 divided by a negative 2 would be a negative 4. We'll graph that one in red. This one, I'm going to add 6x to the other side, so 3y is equal to 6x plus 12. Divide everybody by 3. Y is equal to 2x. Ooh, interesting. Notice slopes are the same. Here's what I now know. At the very least, these are once again parallel lines, right? Parallel lines because they have the same slope. I know at least they're parallel lines. Now, when I go ahead and do the rest of my math here, if I get the exact same y-intercept, we have what we had in the last problem. They're the same line. If this y-intercept is different than this y-intercept, then I have parallel lines. So let's find out what happens. 12 divided by 3 is going to be a plus 4. And there we go. This one has a y-intercept of minus 4. This one has a y-intercept of plus 4. Because my slopes are the same, these are going to be parallel lines. Before I even graph them, I know that I'm going to have no solution. Parallel lines will never intersect each other. And we know, because they never intersect, this system of equations is inconsistent. Awesome. Well, let's just go ahead and graph these guys. Why not? I'll do this one in green. Let's throw these bad boys up there. Negative 4. 1, 2, 3, 4. Awesome. My slope is 2, so rise of 2, run of 1. Up 2 over 1. Up 2 over 1. Up 2 over 1. Up 2 over 1. Yes. Down 2 and back 1. Down 2, back 1. Down 2, back 1. Go ahead and extend your line all the way through the graph, put arrows on either end so I know you know. That line just keeps going. My next one, green, plus 4. 1, 2, 3, 4. It has the exact same slope. Up 2 over 1. Down 2 and back 1 does the exact same thing. Works so well. Let's do it a couple more times. Down 2 and back 1. And connect those points with a line, and that's exactly right. But my graph just confirms what the equations tell me. I have parallel lines. Those lines will never intersect. Therefore, I have no solution. There is no point of intersection, and this system of equations is inconsistent. Guys, that is really good work as far as graphing goes, but this is an algebra class, and as important as graphing is, we want to be able to do the algebra. Plus, the algebra is generally a little bit faster. So, head on over to the next page of the notes. We'll take a look at some algebra, and I'll meet you over there.